Yeah.
I'm pouring my tea as we speak.
Mm-hmm. And I'm making this dramatic leap from coffee to tea because it was suggested. So slowly but surely. Okay, so yay, today is March 4th. I can't believe we're in March already. We're going to start looking at complex numbers. Last class, we spent a bit of time looking at those applications, those word problems. That's what's in that homework 1.3 that's due on Tuesday. Homework 1.1 and 1.2 are due today. Hopefully we've gotten all of the questions involved with those answered. Homework 1.4 is due a week from today, and that's the one on complex numbers. Before we get started, does anybody have any questions on anything? Does anybody want to look at any of those My Math Lab assignments or anything?
Can we go over number 26 in homework 3?
Sure. Let's see. I've got to find the assignment manager. You want homework 1.3, question 26? I didn't think is this the right assignment?
No. Sorry, I meant 1.2 with linear equations and.
Okay, all right. I was thinking I didn't give you guys 26 word problems. That would be brutal. I thought 17 was bad enough. And so but of course I'm trusting you more than I trust myself. Isn't that always the case? Okay, so question number 23, did you say?
26, please.
26, okay. And so in question 26, you're asked to evaluate x squared minus x for the value of x satisfying. I got to turn my mouse into a pen and decide which of the two styluses wants to work today. I'm sorry for the hesitation. Satisfying 8 times x minus 2 plus 2 equals 8x minus 2 times 2 minus x. Well, what we want to plug in for x to evaluate are the values that make this equation true. So the first thing that we need to do is solve this equation. Whenever you solve an equation, the first thing you want to do is simplify. Life's simpler if you simplify first. Distributing on the right, I get 8x minus 16 plus 2. And then combining, that gives me 8x minus 14. There was the left. On the right, distributing, I get 8x minus 4 plus 2x. And combining, that gives me 10x minus 4. With me so far? And doesn't that look much simpler than what we started with?
Yes.
Now what we need to do is get all of our variables on the same side of the equation. I'm going to subtract the 8x from both sides because I've found through the years that if you smooth the smaller quantity, you're more likely to end up working with positive numbers. So that gives me negative 14 equals 2x minus 4. And now is it obvious I'm going to add 4 to both sides? Gives me negative 10 equals 2x, and then dividing, I get x equals negative 5. And what makes this one a little bit dicier is I'm not done yet because they didn't tell me to solve for x. They told me to find the value of x that satisfies that and then substitute it into x squared minus x. And so if I take negative 5 squared minus negative 5, that gives me 25 plus 5. And so I think the value that they're looking for is 30. And so I'm guessing that solving the equation wasn't bad. I'm guessing that substituting isn't bad, but recognizing the fact that you had to do both with this problem makes it a little bit more challenging. Are you better?
Yes, thank you so much.
You're welcome. Does anybody want to look at any other from any of the other homework questions before we pick up with complex numbers because it's going to be a shift in gears today. Okay, I'm not a patient person, so waiting is painful for me. Have I waited long enough? Are you guys all right?
Yeah. I'm trying to I'm logging into the homework right now. I think it was on we had to do 1.1 and 1.2 for homework today, right? I think it was the second one, and it was like one of the last questions. It was a word problem. And it had a graph. It had a graph in it.
Okay.
Here, I'm pulling up the homework right now. It was like 26, I think it was. It was the last problem on like 1.2.
I think the problem that you're referring to is in 1.1, because 26 on 1.2 is what we just did.
Oh, we did? Oh, sorry.
Yeah. So let me look at the preceding assignment.
Oh,
No, 1.1 only has 17 questions.
hmm.
But this is the question I think you're referring to, yes?
Yes, that is it.
Okay. The graph shows the percentage of high school seniors who used alcohol and marijuana during the 30 days prior to being surveyed. The data can be described by the following mathematical models. So we've got these two models here. Where N is the number of years after 1980. A is the percentage of seniors using alcohol, and M is the percentage of seniors using marijuana. Use the appropriate line graph to determine the percentage of seniors who used marijuana in 2009. Well, 2009 would be that last value on the table. So I guess this question was put in the textbook probably in 2010. We were looking for the number who used marijuana. And so reading there, I would get from the graph, does everybody see 20%?
Yeah, I see that.
That they ask us to do is use the appropriate formula to determine the percentage of seniors who use marijuana. And so now this time, rather than using the graph, they want us to use the formula. The formula for marijuana is M equals negative 0.5 N plus 25. Well, we said N is the number of years after 1980. So if I take 2009 and minus 1980, I get that N is 29 years. And so now I'm going to plug in 29 for N. And I'm going to be lazy and not do that multiplication in my head, although I think that turns out to be something like 10.5, but let me just double check to be sure. Negative 0.5 times 29 plus 25 gives me, 10.5. I was off. And so the answer here is 10.5. So first they want you to use the graph, then they want you to use the formula. And then again, the idea that mathematical models and formulas, what did I do? Oh, I think I just typed it wrong. I put the decimal, did I not put the decimal in? No, I put the decimal behind the 5. There we go. Does that look better? There you go.
Yeah, that looks better.
And now it says, does the formula underestimate or overestimate the actual data? Well, the actual data was 20%. And so the formula is lower, so it underestimates. And when I take the difference, I believe that it underestimates it by 9.5%. And then the last three parts of the question ask you to do the same thing. Instead of using the information for marijuana, using the information for alcohol. And so they want you to interpret the graph, read the values off the graph, and then compare it to this linear model that was developed and see what the difference is. Better?
Yeah, that's better.
Okay, what part was sketchy, if you don't mind my asking?
I was just doing, I think I was just plugging it in wrong. I was plugging in the wrong numbers.
Okay, just be careful. Again, I think with the stuff in this graphing section and, the stuff in especially 1.3 or anything where it's a word problem, the key thing is to really just take your time and read carefully. I know that sometimes I'm also guilty of trying to get through it quickly and just skimming the problem and missing things because I skimmed it. Take your time to read carefully. Okay?
Yep, thank you.
You're welcome. Does anybody want to look at any others? If not, I have to apologize. I noticed a few people came in. I had to let people in from the waiting room, but my Chromebook has fallen asleep, so I'm not going to tweak the attendance now. If you came in late, please remind me at the end of class. So today we're going to introduce the idea of imaginary and complex numbers. And before we define them, let's look at what the need is for them. Before, when we did something like the square root of -4, we said that it does not exist. And it doesn't exist because it's not a real number. And so there are equations that we'll find out that if we restrict our thought process to real numbers, they do not have solutions. And so in order to make something like that exist, we're going to introduce something that's called I. I is usually shown with a sort of script looking lowercase I. And it's going to be defined as the square root of -1. And it's called the imaginary unit. And basically, I kind of think it's cool the way they named these imaginary numbers, because if something's not real, we're going to have to imagine it, and we get that imaginary unit. And what we do is we use it to take the square root of a negative number. In order to do this, we're going to make use of that multiplication property of radicals. And so where I have the square root of -4, I'm going to think of that as the square root of 4 times -1. And so just this one time, I'm going to take the effort of breaking that up into the square root of 4 times the square root of -1. And so that's going to give me 2i. That's an example of a pure imaginary number. Which is a number of the form b times I, where b is real. So if I have a real number times I, it's considered a pure imaginary number. And again, we use it to help us take the square root of a negative. Am I talking too fast? Do I need to pause for a minute before I do a couple more examples, or are we good?
You're good for me.
Okay, thank you. So another example, if I want to take the square root of negative 144, again, if I have a negative radicand, a negative under the radical, when I'm looking at a square root, I'm going to think of factoring out that negative 1. Then I'll take the square root of the 144, which is 12, and the square root of the negative 1, which is I. And so again, if a square root has a negative radicand, we want to express it, we need to express it, not want to. We need to express it in terms of I. So another example, if I ask you folks to simplify the square root of negative 25, what would you tell me that that is?
Be 5i.
Beautiful. It's the square root of 25 times negative 1, which gives me 5i. They can get a little bit more complicated. Instead, if I ask you to simplify the square root of negative 27, well, here I'm going to take the square root of 27 times negative 1, but does everybody recognize that 27 is not a perfect square? And so we're going to simplify that like we simplified radicals in the preliminary section in section P. Can anybody think of a number that goes into 27 evenly that is a perfect square?
9.
So that's 9 times 3 times negative 1. And so the square root of 9 is 3. The square root of 3 is the square root of 3. And then that square root of negative 1 is I. Usually we want to put it in that BI form, but we have a coefficient on I so that the I is at the furthest to the right factor. This idea of taking the square root of a negative, all right. Any questions so far?
No, that seems all right.
Okay, then next thing we're going to do is we're going to look at the powers of I. And I don't mean like magical powers, I mean like raising I with an exponent. So I to the first is defined as the square root of negative 1. And so I to the first is I. If I look at I to the second, that would be taking that radical and squaring it. And haven't we said in looking at operations on radicals that when we square a radical, when we square a square root, pardon me, we just get the radicand. So when I square that, I to the second should give me negative 1. Then when I look for I to the third, well, this one, in order to try to evaluate this, I'm going to think of I to the third as being I to the second times I. I to the second, we just said is negative 1. And so negative 1 times I would be negative I. So I to the third gives me negative I. That reasoning okay so far? If so, the next power is I to the fourth. And in that same way, can I think of I to the fourth as I to the second times I to the second, which would be negative 1 times negative 1 or positive 1. And if I want to carry on with this list, wouldn't I to the fifth be I to the fourth times I, which would give me 1I or I. And then for I to the sixth, can I see that as I to the fourth times I squared, which would be 1 times, let's see, I squared is -1. So I to the sixth is -1. I to the seventh would be I to the fourth times I to the third. I to the fourth is 1. I to the third is -I. So I to the seventh is -I. I to the eighth would be I to the fourth times I to the fourth, which would bring me back to 1. And in the same way, I could keep on going. I to the ninth is I to the eighth times I, which would give me just I. And I could keep doing this on and on and on and on. And you see how I have those 4 different answers and they just repeat. So a couple of things that we want to take away from this. One is that we're going to never leave an exponent on I. And to find a power of I, there's 2 approaches that we can take. We can find the largest multiple of 4. That is a factor of the exponent. And so what do I mean by that? Let's say I have x to the 23rd. The largest multiple of 4 would be 20. So we'd have x to the, I guess it's not necessarily a factor, but the factor of the quantity to the power. So we can think of that as x to the 20 times 3. And I to a multiple of 4 will be 1. I'm sorry. I have to totally apologize. These should not be x's, they should be i's. I to the 20th will be 1. I to the third will be -I. And so that gives me -I. So I guess we don't want it to be a factor. We want the largest multiple of 4 that is less than the exponent. The other way that we can do it is we can divide the exponent by 4. And raise I to the remainder. And so there where I have I to the 23rd, if I think of taking 23 and dividing it by 4, it would go in 5 times, and I'd have a remainder of 3. And so that'll be I to the third, which is -I. They're both in practice the same thing. I know that I initially learned it this way using the remainder, but I also know that students are much less comfortable now with that idea of doing long division to find a remainder. So let's have you folks do one. Let's look at I to the 33rd. Did anybody else get that that would be I? And let's try one more. Let's look at I to the 50th. Did anybody else get -1? You guys are being really quiet. Is this concept okay that your powers of I every 4 would keep on repeating? So we're going to divide out, as many I to the 4ths as we can, because I to the 4th is just 1, and see what's left. Are we all right or no?
I'm
You
following
get-
pretty well.
Everybody okay? And the reason I'm asking is because yesterday, my Monday, Wednesday, Friday section had a little bit of a hard time wrapping their minds around this one. You guys are okay though?
For the first one, I got to square root of -1.
The square root of -1 is I,
Oh, okay.
okay? And
Gotcha.
so you've got it right, but again, we're not going to leave that negative under the radical. When we have the square root of -1, that is I. So you're spot on. Just, put it back in terms of I, okay?
All right, thanks.
We're saying the same thing, just with a different accent. So then if we're all right with those pure imaginary numbers, the next place we're going to go are complex numbers. And it amazes me that these are called complex numbers, because in my mind, okay, we've got those real numbers, the real world. We've got those imaginary numbers. And if you stop and think about it, if you start mixing up the real world with your imaginary world, if you start mixing up your real friends with your imaginary friends, your life gets complicated, right? And so those become our complex numbers. They're when we combine the real numbers with the imaginary numbers. And so they'll be numbers of the form standard form is a plus bi, where a and b are real numbers. And so a complex number has 2 parts. It has a real part and it has an imaginary part. And so it's like taking the sum of a real and an imaginary number. So an example, we might have something like 5 plus 2i. And this would be a complex number. Another example, though, I could have 3 plus 0i. And written in this manner, it's a complex number. But Well, when I take 0 times anything, I get 0. And so this would be equal to 3 plus 0, which is just 3. And so it's also a real number. And in that way, we can think of every real number as being a complex number where the coefficient on I is 0. And likewise, if I had something like 0 plus 17I, well, written that way, it's a complex number. But 0 is still that additive identity. And so when I look at 0 plus 17I, that would add to 17I. And so it's a pure imaginary number. And so in defining our complex numbers to be A plus BI, where A is the real part and BI is the imaginary part, depending on whether A or B is 0, we can see that the complex numbers include all of the real numbers, and the complex numbers include all the pure imaginary numbers. So our complex numbers include all the real numbers. I have no idea why I broke that word in half. And all the pure imaginary numbers. So it's a pretty cool set. It includes real numbers, your imaginary numbers, as well as those that are the sum of both the complex numbers. So far so good.
Yep.
If so, we want to define the equality of complex numbers. And so we're going to say that A plus BI equals C plus DI if and only if. Does it make sense that A would have to equal C, the real parts are equal, and B would have to equal D, the imaginary parts are equal. So the real parts equal. And the imaginary parts are equal. So an example would be if I ask you to solve for both X and Y, if 3 plus XI is equal to Y minus 2I. And again here, I'm setting two complex numbers equal. And so their real parts would have to be equal. So I'd get that 3 is equal to Y. And their imaginary parts have to be equal. So I'd get that X is equal to -2. Straightforward enough?
Yep.
If so, then the rest of today, we're going to start looking at operations on complex numbers. And by operations, I mean things like adding, subtracting, multiplying, dividing, and raising to a power. rule of thumb, in many ways, I behaves like a variable. But we have to remember that we're going to never leave an exponent on I. We need to know those 4 basic powers. And if a square root has a negative radicand, you must put it in terms of I first. So, that having been said, let's start looking at addition and subtraction. In general, if I have a plus bi plus c minus di, when I add 2 complex numbers, again, in many ways, I acts like a variable. And so when I do this addition, I almost think of the idea of combining like terms. I add the real parts, a plus c. I'm sorry, that should have been a plus d. And I add the imaginary parts, b plus di. It's kind of like combining like terms. And if I have a plus bi minus c plus di, I'm going to treat this in the same way that I treat subtracting polynomials. I'm going to keep the first one the same. I'm going to put that 1 in front of the second. And think of distributing a plus bi minus c minus di and combine to get a minus c plus b minus d times I. And so it's just very, very much like adding and subtracting polynomials in one variable. So let's look at an example. Let's look at 2 plus 7i plus 10 minus 6i. And again, I'm going to add the real parts. 2 plus 10 would be 12. And I'm going to add the imaginary parts. 7 plus negative 6 would be 1i. Again, it's very much like combining like terms. Instead, if I have something like 9 plus 3i minus 6 minus 2i, I'm going to take the time to rewrite this so that everybody knows the original problem beyond the one that I scribble all over to do my work. I like to think of just like when I'm subtracting polynomials, putting that 1 in front and distributing that negative 1 so that I got 9 plus 3i minus 6 minus times minus would be plus 2i. And now when I combine what's like, I get 3 plus 5i. So I'm going to give you guys a couple to try. Let's look at 7 minus 2 plus 9i. And let's look at negative 8 plus 3i plus 10 minus 17i. And I'll give you guys a minute to work on that. I'll be back in a second. So, did you guys get 5 minus 9i and 2 minus 14i?
I did.
Great. Next example is just a little bit more involved. What if I have 5 times the square root of negative 8 plus 3 times the square root of negative 18? These are, when you have that negative radicand under a square root symbol, you want to put them in terms of I first. And so that'll be 5 times the square root of, that would be 8 times negative 1. And does everybody recognize that I would be able to simplify radical 8? I can think of that as the square root of 4 times 2 times negative 1. So that'll give me 5 times the square root of 4 is 2 times the square root of 2. And the square root of negative 1 is I. So that gives me 10 radical 2i. In the same way, where I have the square root of negative 18, first I'm going to factor out that negative 1. And then 18, largest perfect square that divides it evenly would be 9 times 2 times negative 1. So that gives me 3 times the square root of 9 is 3 times the square root of 2. And then the square root of negative 1 is I. So that gives me 9 radical 2i. They both have a factor of I, so we'll have a purely imaginary number. Adding 10 radical 2 plus 9 radical 2, again, they're like radicals, so I can add them. The radical part will remain the same. And just like before, we'll add those coefficients to get 19 radical 2i. Let's have you folks try one like that. Let's look at, let's say, the square root of negative 75 minus the square root of negative 300. Now be quiet for a minute. Did anybody else get -5 radical 3i? Are we okay with that one? Any questions?
No, no questions.
Okay. Then the next place that we're going to go is we're going to start looking at multiplying complex numbers. And again, I behaves very much like a variable would. When we do this multiplication, we have to remember to distribute or FOIL as needed. Again, that idea that we never leave an exponent on I. And if we have a square root with a negative radicand, we have to put it in I first. So multiply, use your multiplication facts, use your exponential rules for multiplication. If you need to distribute or FOIL, but then remember that we never leave an exponent on I. Remember our powers of I. I to the first is just I to the second would be -1. I to the third would be -I to the fourth would be 1, and it repeats from there. And if we do have an expression with square roots containing a negative radicand, it's very important that we put them in terms of I first. Otherwise, you'll get the wrong answer. So let's look at some examples. Let's first take the product of two purely imaginary numbers. If I have 5i times 7i, well, there's no addition or subtraction here. There's no need to distribute or FOIL. I'm going to just multiply. 5 times 7 would give me 35. I times I is I squared. But I have to remember that I squared is -1. So here my answer is -35. Next example. If I have a product of a real number and a pure imaginary number, 9 times 2i, can think of using that associative property to regroup. The 9 times 2 would give me 18i, and I'm done with them. Next example, we're going to again take the product of two purely complex numbers, but it's going to look a little different. We're going to have the square root of -2 times the square root of -18. And again, you can't just go through and multiply this first. You have to put them in terms of I. So that's the square root of 2 times I. And I'm going to multiply that by the square root of 18 times I, just taking that square root of -1 out. I know some people might want to simplify that radical 18 first, but sometimes I'm lazy and I leave that level of simplification till the end. Radical 2 times radical 18 would be radical 36. I times I would be I squared. And so that gives me 6 times -1, or -6. Please realize if you would have tried to multiply before you put it in terms of I and multiplied those radicands, you would have gotten a different answer. With these, it's very important that we put them in terms of I before we do anything. That went all right.
Yeah, that's okay.
Then next one, let's look at a pure imaginary number, 8i, times a complex number, 2 minus 7i. And again, going to reiterate what I had said before. In many ways, I behaves like a variable. If that were an x instead of an I and you saw a product like this, would everybody think the first thing that I need to do is distribute? Does everybody see the need for distribution there? So the
Yeah.
8i times the 2, great, is the 16i. The 8i times the minus 7i would be negative 56i squared. But again, we have an exponent on I. We don't want to leave that. We'll replace I squared with negative 1. So that gives me 16i plus 56. And usually in my labs, that's correct, but they're not going to accept it in that way because they usually ask you to express either in standard form or in A plus BI form, which means they want the real part first and the imaginary part second. So my final answer here would be the real part is 56 plus the imaginary part is the 16i. Straightforward enough?
Yeah, that's straightforward.
Then next ones, we're going to look at the product of two complex numbers. If I look at 2 plus 3i times 4 minus 5i, I'm going to treat this like I would treat if those i's were a different, if those i's were a variable instead of that basic imaginary unit. Does everybody see what we've got here is the product of two binomials, and we would have to either distribute twice, or I know some of you like to use that box method. I grew up using FOIL, so I'm going to use FOIL, first, outer, inner, last. First, 2 times 4 is 8. Outer, 2 times negative 5i would be negative 10i. Inner, 3 times 4i would be 12i. Last, 3i times negative 5i would be negative 15i squared. Simplifying this, that'll give me 8. Combining the 2 in the middle would be plus 2i. But then we have to remember with that last one, I squared is negative 1. So that gives me 8 plus 2i plus 15. And so in standard form, 8 plus 15 would give me 23 plus 2i. Is everybody all right if I do that by FOIL? Did anybody want to see that one with either the repeated distribution or building that box? Not hearing any complaints, I'm going to give you folks one to try. Let's look at 1 plus 7i times 13 minus 2i. And take your time to multiply that out and let me know what you get. I want to give you guys a heads up. This surface is beginning to get really hot to the touch. If I disappear, I'll be back in a couple minutes. It'll only happen if it overheats. Hopefully it won't. For this one, did anybody else get 27 plus 89i? First, outer, inner, last. Gives me 13 plus 89i. And again, that I squared is -1, so that changes into positive 14, which takes me to that 27 plus 89i. Next example is kind of fun. And it's going to lead us to a new definition. Next example, let's look at 4 plus 3i times 4 minus 3i. And take your time to work that out and let me know what you get. Did anybody else get 25?
Yes.
I took the time to FOIL it out, and in doing so, whoops, I miswrote. The two middle terms cancel each other out. Does anybody notice that what we've got here is like what we were talking about previously with the sum and difference? We have the same terms, just one's a plus sign and one's a minus sign. And so in order to multiply these, we could have just taken that shortcut and said that it's the first term squared minus the second term squared, which would have given us 16 minus 9i squared, which again would have turned into that 16 plus 9 or 25. And that relationship between the sum and difference becomes very important when we multiply complex numbers. And so they're given a name, and they're called very much like when we were looking at a fraction with a binomial radical in the denominator, we use that word conjugate. We're going to call these complex conjugates. And they would be a pair A plus BI and A minus BI. They're like, again, taking the product of the sum and difference of two terms. And when I multiply them, A plus BI times A minus BI, because it's the sum and difference, that will always give me A squared minus BI quantity squared, which will always be A squared minus B squared I squared, which will always be A squared plus B squared. And so the product of a complex number and its conjugate will always be real. The product of a complex number and its conjugate is always real. So let's say I have 7 plus I times 7 minus I. What's that going to give me? Did anybody else get 50? I'm going to think of that as 7 squared minus I squared, which will be 49 minus negative 1, which gives me 50. Where you do have to be careful when you're working with complex numbers is looking at the powers of complex numbers. When I say powers of complex numbers, I don't mean like superhero powers. I mean like raising a complex number to a power, putting an exponent in a complex number. And so I'm going to look at something like 2 plus 4i squared. If you can remember that rule for squaring a binomial, you could apply it here. But I think for most people, it's easiest to think of it as repeated multiplication. And so in terms of repeated multiplication, that would be when I'm squaring that 2 plus 4i times 2 plus 4i. And then we'd have to multiply that out. 4 plus 8i plus 8i plus 16i squared, which would give me 4 plus 16i. I squared is negative 1, so minus 16. So in standard form, that would be 12, negative 12, pardon me, plus 16i. And so if I were to try to raise that to a higher power, something like 2 plus 4i quantity cubed, well, that means I would be multiplying it by itself 3 times. I'd have to multiply these two, which I did already above. And so that would give me the negative 12 plus 16i. And then I'm going to multiply that by the third factor of 2 plus 4i. And again, I would use either repeated distribution or FOIL. First would be negative 24. Outer would be minus 48i. Inner would be plus 32i. Last would be plus 64i squared. So that would give me negative 24 minus, what is that, 16i. And then that I squared, again, is negative 1. So that gives me minus 64. And so the final answer would be negative 88 minus 16i. And there isn't a shortcut for those. You just have to think of doing that repeated multiplication. How are you folks with this idea of multiplying? And again, remembering we never want to leave I squared. I guess had I not simplified, somewhere in here I might have gotten an I cubed. But again, I don't want to leave that exponent on I. And if we simplify as much as possible before we go on, again, the idea that simplification makes your life simpler. Multiplication, all right.
Yes.
Yes, great. Then that leaves one more thing that I'd like to look at today. And let's see, we've added subtracted, multiplied, raised to a power. The next thing that I want to look at is division of complex numbers. And I'd like to divide this into two separate types of division problem. The first that I'd like to look at is how to divide complex numbers by a real number. Something like if I have a plus bi, my complex number, over a real number c. And again, this behaves very much like if we were dividing a binomial by a monomial, if that last number, the denominator is real. And so we have a plus bi over c. Both the a and the b are over c. So I'd write that as a over c plus b over c. And then usually we take that I out and take the fraction b over c as a coefficient on I. So this would be in your standard form. So for example, if I have 6 plus 8i over 2, well, I have to think that I have to divide the 6 by 2, and I also have to divide the 8 by 2. So that would give me 3 plus 4i. And again, I didn't say it, but when we divide that 8 by 2, we do not lose the I. Another example, if I have negative 2 plus the square root of negative 28 over 2. Again, first thing I need to do is I need to simplify the radical, putting it in terms of I first. So when we have that square root of negative 28, can everybody see 28 as 4 times 7? 4 is a perfect square, 7 is prime. And then I also have that factor of negative 1. So that would give me 2 times the square root of 7 times I. So I've got negative 2 plus 2 times the square root of 7 times I. And again, in our original problem, we were dividing that all by 2. And so negative 2 divided by 2 is negative 1. Plus 2 radical 7 divided by 2 would be radical 7. And we'd keep our I. That one all right? Not hearing any questions? The next
Yeah.
place. Question or no? We good?
Yeah, I was just saying we're good.
Okay, thank you. Next place we're going to go then is to divide a complex number by a complex number. And you remember when we were working with radical expressions, with radical expressions, we said we didn't want to leave a square root in the denominator. Well, the equivalent here with complex numbers is you do not leave an I in the denominator. And the way we're going to get rid of that I in the denominator is just like when we had a binomial radical expression in the denominator, we multiplied the numerator and denominator by the conjugate. With complex fractions, what we're going to do is we're going to multiply both the numerator and the denominator by the complex conjugate of the denominator. So for our first example, let's look at something like 3/4 plus 3i. Again, we're going to focus on that denominator. If we've got 4 plus 3i, the conjugate would be 4 minus 3i. And again, when we do this, we want to change what it looks like, but not what it equals. So whatever we multiply the denominator by, we've got to multiply the numerator by the same thing. Again, because we're multiplying by something over itself, we're multiplying by 1. In the numerator, does everybody see the need to distribute? So 3 times 4 would give me 12, minus 3 times 3i is 9i. And we chose the conjugate for the denominator because we realized that when we multiply something by its conjugate, that's sum and difference, it's the first one squared minus the second one squared. And so that'll give me my 12 minus 9i over 16 minus negative 9 will become 16 plus 9. And so that gives me that 12 minus 9i over 25. And now what we've got is something like what we did on the preceding page, but we were dividing a complex number by a real number. And so we want to make sure that we divide both of the terms in the numerator, both the real part and the imaginary part by that to put it in standard form. So in standard form, we'll put the 12 over the 25 minus, we'll put the 9 over the 25 times I. And so again, we want to go there to put it in standard or that A plus BI form. What do you think? Let's look at 3 more examples, each gradually getting a little bit more involved. Before we do that, does anybody have any questions on this?
No, I'm all good.
Okay, thank you. So next example, let's look at negative 6i over 3 plus 2i. Again, I've got a complex number in the denominator. It's a binomial. And so we'd have to multiply both numerator and denominator by the conjugate. And so what would we be multiplying them by?
3 minus 2i.
Beautiful. So we're going to multiply both numerator and denominator by 3 minus 2i. I always take the time to show that because I want to make it clear to myself that I'm multiplying top and bottom by the same thing. So I'm just multiplying my fraction by 1. In the numerator here, again, we need to do that distribution. So negative 6i times 3 is negative 18i. Negative 6i times negative 2i. Let's see, negative times negative is positive. 6 times 2 is 12. I times I is I squared. And I'm going to just simplify that numerator a little bit more. I squared again is negative 1. And so that'll give me negative 12 minus 18i. In the denominator, because they're complex conjugates, because we're taking the product of the sum and difference, it's going to be that first term squared minus that second term squared, which is going to give me 9 minus 4i squared would be 9 plus 4. And so that becomes that negative 12 minus 18i over 13. But again, they want you to separate that. Usually they ask you to separate that into a plus bi form. So we'd say that's negative 12 over 13, the real part, minus 18 over 13 times I. Let's try another. Is everybody okay with that one? Let's have you folks try 3 minus 2i over 7 plus 3i. And I'm going to be quiet for a couple minutes and see what you guys get.
Think your signs are wrong.
Yeah, I think so too. I'm sitting and thinking this is not right. And what the heck did I do? And it was because I didn't put the minus in there. So that's going to change some of my signs here. Thank you. Knew something was off. Did anybody else get 15 over 58 minus 23 over 58i?
Yeah, I did.
Great. Then one more. What if I have 11 plus 3i over 2i? I'm not going to just put each of those over 2i. I've got to rationalize this denominator. And so does it make sense that the conjugate of 2i would be the conjugate of 0 plus 2i? And so what we're going to do is multiply both numerator and denominator by negative 2i. In the numerator, I'll get negative 22i minus 6i squared. In the denominator, I'll get negative 4i squared. And then recognizing that I squared is negative 1, that'll turn into, let's see, negative 6 times negative 1 is positive 6 minus 22i. And negative 4 times negative 1 will give me 4. Now we'll separate that into 6 over 4 minus 22 over 4i. And hopefully everybody recognizes that both of those fractions reduce. So that'll give me 3 halves minus 11 halves i. Is that all right? Any questions? And
Questions?
pardon?
I said I had no questions.
Okay. Which now I am in a quandary because this took a class and a half on my Monday, Wednesday, Friday class because their classes are shorter than yours. I expected getting to this point to take the entire class today, and it didn't. We could go on and start looking at that next section that deals with quadratic equations, but I really would be much more comfortable doing that if I knew that you guys had fully mastered complex numbers first. And so I guess in terms of new content, we're going to stop here. And I'm going to beg you, I don't see you again until Tuesday. I know that going back to the homework, this is not due until a week from today. If you could please try to complete this one by the 9th with the word problems, by Tuesday with the word problems. You know, when we go on and start looking at quadratic equations and equations, higher degree equations and radical equations, it'll make things flow a little bit better. Are you guys sure you don't have any questions on any of what we've done today thus far?
I'm good.
Okay. Then we could call it a day, or I could go back and ask, does anybody want to revisit any of the homework 1.3, the word problem homework? I'm not hearing anything. Does that mean you guys want to call it a day? Even though it's way too early to end class, we're like 20 minutes early. That never happens. Although I guess usually I keep you guys late, so it balances out in the long run. I'm gonna stop recording.